So we can start. So my name is Piotr Gawron. I'm not okay. So I'm not usually introducing these talks, but I was asked to be replacement and to present this talk. So first of all, today's talk is the 12th episode of Warsaw Quantum Computing Group meeting. And the subject is Grover's search algorithm for max-cut problem, presented by Adam Glos, who is my colleague from my ex-institution, Institute of Theoretical and Applied Informatics of Polish Academy of Sciences in Gliwice. So first of all, we would like to thank our sponsors, Daftcode, that is providing us with support. There are some gadgets you can take from Daftcode, the banner, and of course Codecool, who is the school of coding. As far as I know, I learned it during the last meeting. Unfortunately, I cannot tell you more about it, but of course you can ask people around. Okay, so that's basically it. Adam, the floor is yours. And okay, the schedule is that 7:15 the pizza arrives, and we have an after party here in the kitchen. So if you want to ask questions there, I mean more precise questions, of chat up with us, ask anything about quantum computation, you are welcome to do so. Okay, and if you're looking for a job in quantum computation, ask me later, because I have some offerings in Warsaw. Adam, the floor is yours, and I will switch you.
Good morning, everyone. I would like to say a few words about Grover's search algorithm. I think in a little bit different from different perspective that it is usually introduced. In particular, we will try to design actually quantum algorithm for max-cut problem. So, okay, it's working. I will start with briefly explanation of how Grover's search actually works. Then we will deal with some problems that may appear when solving some search problem, in our case max-cut. And then I will say at least about two sources, two communities when you can learn more about quantum computation. So let's start with searching problem. What is searching problem? Imagine you have a database and one element is marked, which means that we want to find it. We can think of it as a database of n numbers. We have some mysterious oracle which knows which element is marked, and we can ask her a question of the form whether the if element is the one that is marked. So we send this element to the oracle. She checks it, and answers us. If the answer is no, then we are giving another element, say the next one. And if the answer is yes, then we are done. That's all. Typically, when we use only conventional computers, classical computers, it requires expectedly n/2 queries. In fact, using quantum computation paradigm, we can do it much faster. Okay, so how we can represent this? Each number has its binary representation. So we can start with all 0 bits, then we can apply nodes, and we can prepare our query. So we're asking whether number 1101 is the one we are looking for. and then Oracle is outputs as an answer. 0 if it's not marked, and 1 if it's marked. In fact, we can make very similar calculation using quantum computers. So, okay, this is not actually correct for now, but we end with proper so-called quantum circuit. We start with not bits, but qubits. Usually, we prefer a different notation for NOT gate. So we again prepare some cat1, cat1, cat0, cat1. It represents exactly the same number. We can put it to the Oracle and get our answer, but usually since quantum computations are reversible, we prefer to use another qubit for storing our answer. So if the element is good, then we apply a NOT gate on an extra qubit. All of the qubits are unchanged. That doesn't change. Not change. Sorry. And on the last qubit, we have our answer. So the first question is whether these formulations gives us anything. At this point, no. It has exactly the same answer. We have obviously to measure it at the end. At this moment, it doesn't give us anything. We still need to generate each possible number and check it at the end. But in quantum world, we have something we call superposition, which says that we can prepare all of the combinations of our numbers, assuming we have its power of 2 for now, and then again process it through our Oracle, and then one element, which is our solution, has 1 on this extra qubit, on the answer qubit. Again, we have processed all of the possible solutions, but this still doesn't give us anything useful for now, because probability that after the measurement we'll get this state is extremely low. It's 1 over n. So it's something that we could say it's a random check, random query. So obviously we have another thing that we need to prepare this complicated state, but this is actually quite simple using a so-called Hadamard gate. It doesn't matter for now what it is. Let's say it's simple. Okay. So let's start. What are quantum gates? Quantum gates are just very trivial, simple operations that act on a qubits. We have one quite simple gate called NOT gate, which simply changes the bit from 0 to 1 and from 1 to 0. We do not have actually a simple quantum gate that changes everything to, let's say, 1, as quantum computations are reversible. But we have a little bit more complicated gates, like control NOT, which is something we could consider as if gate. Because if the first qubit is 0, then we do not do anything. We do nothing. If the first qubit is 1, then we change the second qubit into the opposite one. We just make a NOT, actually. This is why where the name comes, where the name comes, because depending on the controlled qubit, which is marked here as a full dot, we do or do not change, we do or do not perform a NOT gate on a second qubit. But it turns out that we have much more interesting quantum gates, which are, for the example, Hadamard. Hadamard is used for creating a superposition of basic states, as we have actually done before. For example, if we start with 0 qubit, then we have those two. It's not maybe exactly correct, but we have those two states at the same time. It's not really correct because we can usually measure only one of it using the standard basis. But we could consider it as something like a quantum parallelism. Another gate that I will use in this presentation is a Z gate, which changes only one state into -1. In general, I will say it more precisely later, but gates acting on 1 or 2 qubits, like this one, are considered to be simple. Okay, so what's a Grover algorithm? Actually, Grover algorithm has quite simple representation, because we are applying Hadamard gates at the very beginning. Then we apply our oracle and something we call Grover diffusion operator for k times. These are two gates that are exactly the same. There is our solution hidden, and this is some general gate that is independent on our problem. At the very end, we measure first qubits, and hopefully we get our answer. It turns out that if k is only of square root of n of the database size, we can find our solution with probability almost 1. This is something I think I could say just impossible for classical computation, at least assuming we have only finite numbers of cores. But still, we have some problems with what we are with those things. First of all, we don't start with 0, but we start with a little bit more complicated state on the last qubit. Even more interesting is this issue, because note that our oracle changes, applies the NOT on the last qubit, but we do not measure it. The output of this qubit is not important for us. We just need the outputs of the measurement from the first few qubits. Thirdly and fourthly, we need to implement these two gates. One which is our oracle, and one which is a Grover diffusion operator. So the rest of the presentation will be exactly on solving these issues that appears for Grover algorithm. So let's try with the simplest one. With this initial state on the last qubit. Actually, this is not really a problem. We just need to apply these two simple gates, a NOT gate and Hadamard gate. You could it's working now. You could see that if we apply Hadamard on 1, then we precisely have this state. So we just need to prepare from 0 to 1, which is can be done using our NOT gate, and that's all. A little bit more difficult is the second issue. Our oracle applies NOT on the last qubit. it is how it marks that, how it says that this element is interesting for us. However, we do not measure this qubit. And as I said before, this oracle doesn't change, let's say for now, doesn't change anything on this first 3 qubits. So what's happening here is phase kickback. So suppose you start with this state. Let's recall me that this is the controlled qubit, and this is the target. In principle, this is the qubit that should be changed. But it turns out that the target qubit remains unchanged, while the first qubit, the control qubit, has changed its phase on the 1, for the 1 get. This is something I would say very quantum, because it comes from this superposition, and in particular that we can have a minus here. And because of this, because we actually start with this state with minus, we are changing something that is called local phase on qubits above, on the order of first 3 qubits. Because as you can see, this state remains unchanged, we can use a different qubit for marking, which is our previously introduced Z gate. Still, it is not obvious how we should implement this oracle gate. Okay, so I have assigned first 2 issues. We still need to deal with the composition of these 2 big gates, of oracle and Grover diffusion operator. Okay, so first of all, what is the composition for us? We say that quantum circuit is decomposed if it only consists of single qubit gates and of control node gates. As an example, let us consider Toffoli gate. Toffoli gate is a gate that changes this, applies not on the 3rd qubit if first 2 are 1s. And it turns out that it can be decomposed in the following circuit. In fact, it can be shown that we exactly need 6 control nodes for implementing this Toffoli. We don't need more, we cannot do less. In fact, this is very important gate. I will need for a moment a generalized N-Toffoli gate when the control is on n qubits, and we have a single target qubit, let's say the last one. It is not actually that trivial how to decompose it. There are several possible decompositions depending on whether we have or do not have additional qubits. Here is a little bit simpler one, which for each n control qubits requires n minus 1 ancillary qubits, additional qubits. This is actually not full decomposition because it is decomposed into Toffoli gates, but using the decomposition that I showed before, we can decompose it further into control node and single qubit gates. Okay, so we can, using this decomposition, okay, I will have this a little bit later. Using this decomposition, we can actually solve our 3rd issue with decomposing Grover diffusion operator. The composition is exactly like this. We start with some Hadamard gates, apply nodes, and we applied this oracle. It actually could be introduced as a control Z gate, but I would say it's a little bit convenient because exactly we need if we have n qubits that we are when we are applying Gaussian diffusion operator, we need n-1 Toffoli gate. Okay, and that was actually I would say simpler part, because now what we need to deal with is with the oracle. How actually we can design a quantum secret for the quantum oracle. The thing is that we cannot provide a general formula here because it actually depends on our problem. If you could say that if element is marked, then we simply don't need to search for it. It is interesting whether this E, where is the solution, depends on some different formulation. And during this presentation, I will present you a decomposition particularly for max-cut problem. Okay, so what is max-cut problem? Suppose we have a graph, and we have two partitions of the vertices. We just color them into two colors. Here it is, I guess, red and let's say brown. Okay, and what we are doing, what we should do, we are counting edges that connects vertices with different colors. Here, I'm not sure whether you see that, but there are blue. So, for the partition on the left, for the coloring on the left, we have 5 edges that are blue, because the only one that is not connecting different colors is that one. Here we have a little bit worse scenario, because 3 edges are only 3 edges are blue. So the question is, whether we can find how to create a partition such that we have as much as possible for a given graph edges that connects vertices with different colors. This is our problem. It turns out that it is NP-complete problem, actually very important one. And usually, instead of coloring, we are saying about partition of the vertices. Okay. So, let's focus a little bit of our representation. We start with partition. So we have 2 sets, such that each node belongs to one set, and they define our colors. So red R set is 1, 3, and 4, and brown S is 2 and 5. But instead of sets, instead of 2-element partition, we can think of it as a function from nodes to the colors. This is exactly the same representation. Furthermore, since we have only 2 colors, we can use just bit. So if node should be red, then it should be say for now a red 0. If it should be brown, it should be a brown 1. We can obviously drop the colors because we don't need them anymore. And since we are searching for a bit string, which is actually a number, we can use it for searching in our Grover search algorithm. Obviously, still we have the problem how to construct our oracle. So, let's start with a simple thing. First, we need to design a method how to check whether the vertices have different colors. What we can use XOR operation. So we have 3 qubits. One for vertex 1, for vertex 2, and another one for storing our answer, for edge connecting 1 and 2. So we have qubits. Okay, and they have colors A, B. Here is initialized to 0. Okay, so what happens if we make our first control node? If A is 1, then here we would have 1. If A is 0, then it still is 0. So here we have A. If you apply a second control node, and then if B is 1, then we change it again. If B is 0, then we again do nothing. We can represent it as a XOR gate. And what happened? If they are both 0, then we do not do anything, and we again have 0. If both are 1, then we apply node twice. So applying node twice doesn't change anything again. But if we apply node only once, then we have 1 as an answer. 1 is our answer. So this ancilla qubit, this separate qubit, we have the answer whether these 2 vertices have different colors. And here is the solution for our graph. First 2 qubits represent these 4 vertices. Here we have our answers, and later we will use this ancilla qubit for storing our final solution. Okay, so you can see that for blue edge, the top one, we are precisely applying this control node on the first 2 qubits, and we store our answer here. We are doing exactly the same for each edge. So for each edge, we will need a separate qubit. So we will let's start with a simpler question, whether we can find a coloring such that every edge connects vertices with different colors. We have just simplified our problem. We are applying our edge checking. These are those first AF gates. And at the very end, we apply n Toffoli gate, 4 Toffoli gate. Because if E12 and E23 and E24 and E34 is 1, then we apply not here. So our answer will be 1 if all of the edges connect vertices with different colors, and 0 otherwise. What we need to do, we need to mark our element, which is changing the phase for 1, and we need to undo all of the operations except Z, so we can go back to our representation that we start with. This is so we could, let's say, transfer this local phase change, this minus, to the top. And this is actually our oracle, which checks whether all edges connect vertices with different colors. Okay, so the question is whether we are done. No, actually, we would be ready if we would like to solve the problem with checking all edges. But the thing is that it is a very, very simple problem. Why? Because it's equivalent to something called bipartiteness checking. This is just checking whether graph is bipartite. Our algorithm, which is better than classical random search, have complexity square root over n to the over 2 to the number of vertices. But the best classical algorithm have this complexity is actually in the worst case scenario. So we actually haven't done anything efficient for now. But actually, this wasn't the problem that we were trying to solve. We didn't want to check whether all edges can connect vertices with different colors, but how much edges can connect different colors. So what we need, actually, we need a method for counting our edges and then comparing them. Okay, so this is just a general scenario. First, we need to use extra qubits for storing our number of edges that are blue, that connect vertices with different colors. We need to apply our check edge for each edge. And then we need to use our something we call for now add there gate, so that we will update this number of these edges for each edge. We just simply add, we are just making +1 or +1, 0. Okay. Suppose that this edge connects vertices with different colors. Then here we will have 1, because we are applying a NOT gate. So to this number, we are just applying 1. If it's 0, we're applying 0. Unfortunately, we cannot check it before, because we would need to measure the qubits, which are prohibited before the final measurement, because it changes our computation. But we can just make always an under. After checking each edge, we need to check our number and apply a NOT at the very end, on the last qubit, for all numbers that interest us. Which numbers are interesting, I will say a little bit later. Then we again apply our Z, so that we could, we mark our elements, and then we undo all of these operations except the Z gate. Okay, so now what we are missing, because we have defined already the check edge, these are these XOR operators, as I showed before. We just need to design our adder and design our gate for checking, which checks the number. Okay, so let's start with adding. There's a general actually adder gate, but we will need only a simpler one, because we are just adding 1 to the number. So it turns out that the form of this adder is as on the top right corner. This is just one part of our computation. Because if our number is, let's say, 1011, when adding 1, then this is our A, and this is our B0. Here we will have our answer, which is a sum, and if we have two ones, then we need to move a single one for the next bit. And this is our cin, which actually will be transformed later just to the cout. So for 3-digit number, it will look like this. So for first bit, which doesn't change A, and B0 prime is changed dependently on the output of A. And here we have our cout, which is used for a next adder, which changes B1 into B1 prime, again which produces a cout. Here, because we have 3 digits only, it is just moved to the last qubit for B2 prime. So this is how we can add one to a given number, which is what we needed here. This is precisely the adder. Note that for each digit, for each bit, we will need an extra qubit, which will just store our cout cin value. Okay, so last thing that we need to resolve is how we check our number. There's a small problem because max cut is an optimization problem. So we just want to search over all partitions, let's say argmax, of the number of edges such that one is for the first set and the other is for the second set. But we do not know not only this partition, but also the number of these edges. So it is difficult to say which number is interesting. What we can do, we can make a binary search. We can start with a question whether there is number such that is greater at least 4. If there is, we can it's not written here, but let's assume that there is at most 8 edges, 7 edges, sorry. Then we can search for graphs for numbers which are greater at least 6. If there is, we are checking for 7. If there is no such number, we are searching for a 5. At each level, we need a separate Grover search algorithm. In general, it is still quite small, even for a large number of edges. But we have only bits. We can ask similar questions using a binary notation, where 4 is just changed into 1, 0, 0. There was a 6 here. So it's changed into 1, 1, 0, and so on. But we can relatively easily check our bits with the following form. If we want to find number that is greater with 4, which is 1, 0, 0, we just want to check whether there's a number that has a 1 at the very beginning and absolutely anything on last 2 qubits. It can be 0, 0, it can be 0, 1, it simply doesn't matter. Because each number would satisfy this equality. For k at least 6, which is 1, 1, 0, we need to have 1, 1 here, and absolutely anything here. It can be 0, then it would be 6. It could maybe 7, then it would be 1. So why I'm saying is because checking bits is simple. We just need to apply special Toffoli gates. For 4, we just need to check whether the B2 is 1, then apply a control node. Here, we need to check these 2 bits. And if we know, for example, there was a 5 here, which is 1, 0, 1, then we just need to apply node before, check whether all are 1s, and just recover the previous bit. And again, apply the node. And actually, that's all. Because we have check edge, which is our XOR operation I told you before. We have our other, and we have number checking. We know how to apply Z gate. Undoing is simple in quantum computation. Okay. So we have designed our oracle. We have solved all our problems with designing a quantum circuit. So the thing is, what are we waiting for? We have quantum computer, we have a quantum algorithm, we can run it. This is not that simple. Why? Because the biggest currently quantum computer have only 53 qubits, which is too small. There are obviously another issues that it has to all quantum circuits need to be fitted to a special topology. The computers are noisy. Obviously, we have bigger computer, but again, there's a problem because it is not actually a computer. This is very special machine which is designed for a very special paradigm of computation called quantum annealing. Because of that, we simply cannot apply Grover's search algorithm on the wave. Okay, so what's actually our cost? Let's take a graph with 5 qubits and 10 edges. So we need 5 vertices for storing our answer. We need m edges for each check edge. Which was of this form. We need log of m of qubits for storing our number. We need this long formula just used for others. These qubits are just wasted. And just one for marking our element. For this graph, it sums up to 46 qubits. Note that all of possible partitions, formula for all partitions is 2 to the 5, which equals 32. This is something that we can just brute force on a classical computer. There's another thing, because we for quantum computation, we also need to count our gates, because we can only perform a very short computations. So we need 2 MC nodes for each. Okay, we need 2 MC nodes for all edges. Actually, not for each edge. Plus extra for undoing our operations. As here, we need 1 Toffoli gate and 1 node for each other, for each edge, for each bit, which is actually a lot. Okay, let us consider a simple case when we only check one bit for number checking and one Z gate. So again, for this graph, only Oracle requires 86 CNOTs and dozens of single qubit gates. But this is just for one Oracle, which needs to be repeated for, let's say, for n equals 5. I'm not sure how much it is, about 6 times, plus Grover diffusion operator. Okay, and that's all actually. But it's really, believe me, it's really too much for quantum computers. The thing is whether we can improve this, whether we can need much less gates or qubits. The answer is yes, we can improve this. The improvement is still too small, so we could run it on a quantum computer. But yes, we can improve it. For example, for each adder, we do not need this control node for our last bit, because we can consider this as just moving the answer from the one by last qubit to the last qubit. So we can just skip that. We saved one CNOT, which is actually not that much, but what's more important, we saved one qubit. Secondly, what we can do, we can skip some operations when adding numbers. This is slightly more complicated. So suppose that we know that B0, B1, B2 is either all zeros or 0, 0, 1. Toffoli applies not only if these two bits are 1, but we know that this bit is 0. So this gate won't do anything. Just a moment. Okay. And now we do not need this qubit for this addition, because again we are just moving forward the state from this gate to this gate, and this qubit to this qubit. So we can remove this control node, and instead of negating this qubit, we can negate this one. Actually, this simplification saves a lot of quantum gates. Unfortunately, it's not enough to run it. Second one, a little more tricky, is to simplify our addition, our decomposition of our addition. So let's actually about 20 slides before, I presented you a decomposition of Toffoli gate. For adder, we need to apply one control node at the very end, but it turns out that these two control nodes cancel each other, because these are exactly the same. If we apply node here and apply node here, then it's like we didn't do anything and done anything. So we can cancel it out. Again, 2 CNOTs saved for each adder. The last simplification that I will show you today is, I would say, the most tricky one. It comes from that we actually do not need to preserve our local phases. What's happening here? Suppose that we have our Toffoli gate. And we start with, let's say, state 1, 1, 0. Then Toffoli gate should output as 1, 1, 1. Obviously, the tensor product between them. And this is how Toffoli gate should work. Let's say that we allow our Toffoli gate to change for each basic state by some local phase. This is again very quantum. It turns out that if we allow this change, then we can save another control node in our decomposition, which is again a huge improvement. Unfortunately, we cannot do it for arbitrarily Toffoli that appears in our quantum circuit, but still we can use it quite often because we can use it for each adder. Why? Because undoing all of these operations again corrects this local phase change. And Z gate just changes it by P. This is quite complicated improvement, I must say. So this is why I put it at the very end. But again, it saves actually a lot. Okay, so I just wanted to put some final remarks. We can make some other simple improvement corrections of our quantum circuit. It is very difficult to show it here because just our it is just too small to present a whole circuit. And secondly, we can significantly reduce the number of qubits required by applying some additional control NOT gates. We actually need a lot of these gates, but if we would have a quantum computer that would won't have much qubits, won't have many qubits, but will allow us to perform some much longer computations, then it would be very useful. Third thing is that Grover, it's something because I liked a little bit before, because Grover algorithm requires actually this number of oracle repetitions, where M is the number of marked solutions. In fact, we need to know this number before, but we can do this by something called quantum counting, which is actually very, again, efficient. It has a very similar complexity like Grover search. Okay, so this is all I wanted to say about Grover search. What I would like to say is that there are two communities, very friendly communities, I must say, that appeared. One is the IBM community, Qiskit community also as well. Then it is English spoken community, which where you can ask anyone actually about anything that is something somehow connected to quantum computation. I must say I'm using all the time, both for searching for an answer and for putting some answers. Secondly, there's quite a new organization called QPoland, as a part of international organization QWORD. We also we're still organizing, but we also have a Slack And what's maybe a little bit more important, we are planning to use a Polish language in this Slack. So if you have some problems with English, or you know anyone with such difficulties, then I can honestly encourage to search for CoPoland. Okay, so that's all I wanted to say. One thing is that this presentation is based on my experience on IBM Quantum Challenge, where we actually aimed at solving efficiently in number of gates max cut problem. As far as now, there will be another edition next year, so I encourage everyone to attend. And actually, that's all. If there are any questions, then I will be happy to answer them.
Questions? Anyone? I have a question. So how many qubits and gates you need in order to implement the compressed algorithm?
Oh, I would need to count them.
Approximately, out of your
of order n plus of order of log 2 of number of edges.
That's number of qubits.
Number of qubits, yes.
Okay, and
so it's still actually the lot, mostly because of this one.
Yeah.
But in this, there will be just a lot of gates. So this is not that efficient, unfortunately.
And is it implemented somewhere? Do you have a code?
I personally don't implement this version, but if you search for IBM Quantum Challenge, then there are answers of 10 best solutions. So in particular, you can find solutions there with explanation. So it's actually very, quite interesting. At least for me, it was.
Questions? Okay, not. Let's thank the speaker again. I have some closing remarks. There's still some time for the pizza, before the pizza comes. Warsaw Quantum Computing Group is trademark, as Paweł says. So next time I will be talking about quantum neural networks. I believe a practical approach. I will be showing more code, less networks, less like these nice pictures and less proofs, because I'm more computer scientist than applied computer scientist than theoretician, mathematician nakada. So I will show you some code. Hopefully, I will show how to use something that might be useful. I mean, that could be implemented on an existing quantum computer, and at least in simulation, and hopefully it will be something interesting for you. Okay, so first of all, I would like to thank Paweł for organizing everything. I'm just filling in for him because he's sick now, so he asked me to fill in. There is a couple of links you might be interested in. So this is my link list. So these links are very long, and probably you should just look for Facebook group, I believe, because that's the simplest thing. There are these lectures are available online on the YouTube channel. If you want to watch them at home. Basically, Paweł organizes everything, so you can drag down his email address if you want to contact him somehow. Once again, thanks for the sponsorship. You have these gadgets over there. You can save yourself. They look pretty useful and nice. And thanks for the Codecool for sharing space. The next meeting should be in the space provided by Daftcode. So not here, in another place. We wait for an email if you are subscribed. transcribed from Pavel with all the details. I unfortunately don't know the details. So thank you for your attention, and it's time for the after party. Probably not yet. We have still some couple of minutes. Oh, we should look into